February 7th, 1984. Bruce McCandless stepped out of the Space Shuttle Challenger and did something no human being had ever done before. He let go. No tether, no safety line, no physical connection to the spacecraft. Just him and the suit, floating alone in the vacuum 200 kilometers above Earth. Think about that for a moment. Every astronaut before him had been tied to their ship, anchored by some kind of lifeline. Even the Apollo astronauts walking on the moon had their lunar module a few steps away. But McCandless pushed himself away from the shuttle using a nitrogen jet backpack called the Manned Maneuvering Unit and drifted into open space. He became the first human satellite, orbiting Earth completely untethered. One malfunction in that backpack, one mistake in trajectory, and he would have drifted away forever, a solitary body falling endlessly through the void with no way to return. This was not just a bold engineering test, it was humanity's first true brush with cosmic terror on a personal scale. The photographs from that mission show a tiny white figure suspended against the black abyss of space, Earth curving blue and massive far below. That image should unsettle you, because it shows exactly how fragile we are when we leave our protective bubble. McCandless floated in an environment that offered zero forgiveness. No air, no pressure, no sound. Just a thin layer of fabric and technology between his body and instant death. The void around him was not empty in the comforting sense of an open field. It was overwhelmingly nothing, stretching in every direction without limit, without mercy, without even the possibility of help. Space does not care about you. It does not notice your existence. If something had gone wrong, McCandless would not have fallen or crashed. He would have simply continued moving, drifting slowly away from the shuttle, from Earth, from everything, until his oxygen ran out. Then his body would have kept going, frozen and preserved, orbiting silently for decades or centuries. There would be no dramatic explosion, no noise, no final moment of impact. Just silence and an eternal, lonely drift through a vacuum that has no end. That is what makes this moment more psychologically terrifying than even the moon landings. Neil Armstrong and Buzz Aldrin were pioneers, yes, but they had the lunar module right there. McCandless had nothing. He pushed into the abyss and trusted a machine to bring him back. What he experienced out there is something most of us will never feel but need to understand. When you are untethered in space, you realize that up and down are illusions. There is no ground to fall toward. Earth is not below you in any meaningful sense. It is just another object in space, and you are falling around it at thousands of kilometers per hour. The only thing keeping you in orbit is your velocity. If you slow down, you spiral inward. If you speed up, you drift outward. One tiny push in the wrong direction, and your path changes, and there is no friction to stop you, no atmosphere to slow you down. You just keep going. The silence is absolute. You cannot hear your own breathing outside the suit. You cannot hear the shuttle. You are sealed inside your helmet with only the sound of your heartbeat and the hiss of your oxygen system. The void is psychologically loud, not because it makes noise, but because your brain is screaming at you that you are in a place where you do not belong. And yet, McCandless came back. He fired his nitrogen jets and returned to the shuttle. He proved that humans could work freely in space, untethered, and survive. But what he also proved, intentionally or not, is that space instantly reminds us how fragile we are. We are creatures built for a narrow strip of temperature, a narrow range of pressure, a specific mixture of gases, and a planet with gravity. Step outside those conditions even for a second, and you die. Space does not give warnings. It does not give second chances. It is an environment of absolutes. Floating untethered in that void, McCandless became the living symbol of how small and vulnerable humans truly are when confronted with the infinite. And here is the question that should be forming in your mind right now. If just stepping a few hundred kilometers away from Earth into the relatively nearby vacuum of low orbit is that hostile, that unforgiving, that terrifying, then what does that say about the rest of space? What happens when you look beyond our thin atmosphere, beyond our moon, beyond the edges of our solar system, and into the unimaginable distances that surround us? because the void McCandless floated in is nothing compared to what lies beyond. When Bruce McCandless floated untethered above Earth, you saw how hostile space becomes just a few hundred kilometers away from home. Now take that feeling of exposure and stretch it outward, far beyond his orbit, far beyond the moon, out into the structure of the universe itself. Space looks empty when you glance at the night sky, a few bright points scattered on a black background. But that impression is deeply misleading. The apparent emptiness is not a comforting void. It is a thin surface hiding something overwhelmingly large and structured, a cosmic architecture that your brain is not naturally built to grasp. Astronomers have mapped that hidden structure using telescopes that collect light across the electromagnetic spectrum, and by carefully measuring the positions and motions of hundreds of thousands of galaxies. What emerges from those surveys is not a random spray of stars, but a vast three-dimensional pattern. Galaxies gather into groups and clusters. Clusters link together into colossal threads called galaxy filaments that can stretch for hundreds of millions of light years. Between these filaments are immense cosmic voids, regions that span tens or even hundreds of millions of light years, with very few galaxies inside them. When scientists reconstruct this pattern on a computer, it looks like a glowing web suspended in darkness, a network so large that even the word enormous feels too small. Each bright node in this web is a galaxy cluster containing hundreds or thousands of individual galaxies, and each of those galaxies can hold hundreds of billions of stars. Many of those stars will have planets. Some of those planets may be rocky worlds with atmospheres, oceans, and perhaps chemistry that has begun to climb toward life. Yet when you step back, all of that richness collapses into a faint smear of light along a filament that itself is only one thread among many in the observable universe. The scale jump from McCandless and his fragile suit to a galaxy cluster is so extreme that both levels begin to feel unreal, like different layers in a dream that do not quite fit together. In some regions of this web, the laws of physics as you know them start to reach their limits. Near the centers of galaxies, supermassive black holes twist space and time so violently that the familiar rules of matter and energy break down at their boundaries. At the edges of clusters, dark matter, an invisible form of mass that does not emit light, dominates the gravitational landscape. In the most extreme environments, densities, temperatures, and energies become so high that your everyday intuition about how objects should move or how light should behave simply fails. You have to rely on abstract equations and experimental data, because there is no direct human experience that matches those conditions. And here is the unsettling part. You only see a tiny fraction of this structure with your naked eyes. When you look up at night, you see mainly nearby stars within your own galaxy, and a couple of neighbouring galaxies as pale smudges if you are under dark skies. Almost everything else, all the distant galaxies, filaments and clusters, is invisible without instruments. The darkness between the stars is not empty. It is the darkness of distance and scale. It is what happens when the universe is so large that most of its contents are too faint and too far for your eyes to register at all. Modern cosmology goes further and tells you that even the luminous web of galaxies is not the full story. The ordinary matter that makes stars, planets, and you is only a small fraction of the total content of the universe. The rest is dominated by dark matter and dark energy, components that cannot be seen directly and are known only by their gravitational effects and their influence on cosmic expansion. That means that the bright structures you can map are like the thin frost on the surface of a much deeper and darker reality. The cosmos you imagine from photographs is already a simplification, a filtered version of something stranger and less intuitive than any myth. This is why the universe begins to resemble cosmic horror more than a gentle backdrop for human stories. You live in a reality where almost everything is out of reach, where most matter is invisible, and where the largest patterns are so vast that human lifetimes and human distances become negligible. The part you can see with all your telescopes and detectors is still only the observable slice, limited by the speed of light and the age of the universe. Beyond that horizon, the structure likely continues, with more filaments, more clusters, and more voids that you will never witness. Most of the universe will remain unseen, not because you lack technology today, but because the very rules of space and time prevent that information from ever arriving. When Bruce McCandless floated untethered above Earth, you saw how hostile space becomes just a few hundred kilometers away from home. Now take that feeling of exposure and stretch it outward, far beyond his orbit, far beyond the moon, out into the structure of the universe itself. Space looks empty when you glance at the night sky, a few bright points scattered on a black background. But that impression is deeply misleading. The apparent emptiness is not a comforting void. It is a thin surface hiding something overwhelmingly large and structured, a cosmic architecture that your brain is not naturally built to grasp. Astronomers have mapped that hidden structure using telescopes that collect light across the electromagnetic spectrum, and by carefully measuring the positions and motions of hundreds of thousands of galaxies. What emerges from those surveys is not a random spray of stars, but a vast three-dimensional pattern. Galaxies gather into groups and clusters. Clusters link together into colossal threads called galaxy filaments that can stretch for hundreds of millions of light years. Between these filaments are immense cosmic voids, regions that span tens or even hundreds of millions of light years, with very few galaxies inside them. When scientists reconstruct this pattern on a computer, it looks like a glowing web suspended in darkness, a network so large that even the word enormous feels too small. Each bright node in this web is a galaxy cluster containing hundreds or thousands of individual galaxies, and each of those galaxies can hold hundreds of billions of stars. Many of those stars will have planets. Some of those planets may be rocky worlds with atmospheres, oceans, and perhaps chemistry that has begun to climb toward life. Yet when you step back, all of that richness collapses into a faint smear of light along a filament that itself is only one thread among many in the observable universe. The scale jump from McCandless in his fragile suit to a galaxy cluster is so extreme that both levels begin to feel unreal, like different layers in a dream that do not quite fit together. In some regions of this web, the laws of physics as you know them start to reach their limits. Near the centers of galaxies, supermassive black holes twist space and time so violently that the familiar rules of matter and energy break down at their boundaries. At the edges of clusters, dark matter, an invisible form of mass that does not emit light, dominates the gravitational landscape. In the most extreme environments, densities, temperatures, and energies become so high that your everyday intuition about how objects should move or how light should behave simply fails. You have to rely on abstract equations and experimental data, because there is no direct human experience that matches those conditions. And here is the unsettling part. You only see a tiny fraction of this structure with your naked eyes. When you look up at night, you see mainly nearby stars within your own galaxy, and a couple of neighboring galaxies as pale smudges if you are under dark skies. Almost everything else, all the distant galaxies, filaments and clusters, is invisible without instruments. The darkness between the stars is not empty. It is the darkness of distance and scale. It is what happens when the universe is so large that most of its contents are too faint and too far for your eyes to register at all. Modern cosmology goes further and tells you that even the luminous web of galaxies is not the full story. The ordinary matter that makes stars, planets, and you is only a small fraction of the total content of the universe. The rest is dominated by dark matter and dark energy, components that cannot be seen directly and are known only by their gravitational effects and their influence on cosmic expansion. That means that the bright structures you can map are like the thin frost on the surface of a much deeper and darker reality. The cosmos you imagine from photographs is already a simplification, a filtered version of something stranger and less intuitive than any myth. This is why the universe begins to resemble cosmic horror more than a gentle backdrop for human stories. You live in a reality where almost everything is out of reach, where most matter is invisible, and where the largest patterns are so vast that human lifetimes and human distances become negligible. The part you can see with all your telescopes and detectors is still only the observable slice, limited by the speed of light and the age of the universe. Beyond that horizon, the structure likely continues, with more filaments, more clusters, and more voids that you will never witness. Most of the universe will remain unseen, not because you lack technology today, but because the very rules of space and time prevent that information from ever arriving. So hold on to the image of McCandless as a tiny figure against the void, and now place that figure inside a galaxy, place that galaxy inside a cluster, and then strand that cluster along a filament stretching across hundreds of millions of light years. Ask yourself a simple but disturbing question. If the small patch of space around Earth already feels so lethal and unforgiving, what does it mean that this lethal environment is just one microscopic part of a web that spans the observable universe? You will step back from these scales and ask why, despite all this hostility and incomprehensible size, humans have always looked up, always felt that the sky mattered, long before anyone knew what truly waited in the dark. But a vast web of galaxies, filaments and voids, a structure so large that human intuition breaks under its weight. Now step back in time before telescopes, before physics, before anyone knew the words galaxy or light year. Imagine early humans standing under that same sky, with no idea what stars are made of, yet still feeling that the night above them mattered in a way nothing else did. For those first observers, the sky was not a distant abstraction, it was a tool for survival. Long before written language, people learned to track the motion of the sun, the phases of the moon, and the slow drift of constellations across the seasons. By noticing which stars rose just before dawn at certain times of year, they could tell when floods would come, when winter approached, and when to plant or harvest. The sky became a clock and a calendar written in light. If you misread that clock, your crops could fail. If you ignored the seasons, your group might starve. So paying attention to the heavens was not a luxury. It was a necessity that selected for curiosity, patience, and pattern recognition. At the same time, the night sky became the first map. Before compasses, before global positioning systems, navigators steered by the stars over desert and ocean. The North Star held its position in the sky close to the North Celestial Pole, giving travelers a fixed point to orient themselves. In the Southern Hemisphere, patterns like the Southern Cross served a similar role. Polynesian navigators learned to read entire star fields, wave patterns and cloud shapes to cross thousands of kilometers of open ocean with extraordinary precision. On land, caravans tracked known constellations to move along trade routes. The sky was the only stable reference frame that stretched over every landscape. But survival and navigation were only part of the story. In almost every known culture, myths and gods were written directly onto the constellations. People saw hunters, lions, dragons, goddesses, and heroes traced in the arrangements of stars. These were not random decorations. They were stories that carried explanations, warnings, and shared identity. A bright new star might be seen as an omen. A comet might be a sign of disaster or change. Eclipses could terrify entire societies because they violated the expected order of the sky. When the sun or moon was swallowed by darkness, it felt as if the universe itself were unstable, as if some cosmic power were displeased. The sky shaped religion, fear, and comfort all at once. What is important for you to notice is that humans sensed that the sky held deep importance long before they understood what it physically was. They saw patterns and regularities, but lacked the tools to measure distances or compositions. So they filled the gaps with stories. Those stories were early attempts to make meaning from a reality that felt both reliable and mysterious. The stars always returned, the seasons always cycled, yet lightning struck, meteors flashed, and occasionally something unexpected appeared. The heavens were stable enough to trust, but unpredictable enough to inspire awe and anxiety. Then telescopes arrived, and the comfort began to crack. When Galileo Galilei pointed a simple refracting telescope at Jupiter, he saw moons orbiting another world, proving that Earth was not the unique center of motion. When he looked at the Milky Way, he discovered that its pale band was not a cloud, but a swarm of countless stars. Later, more powerful instruments revealed craters on the moon. sunspots on the sun, and eventually entire galaxies far beyond the Milky Way. Each step outward shattered another layer of human-centered thinking. The universe was larger, older, and more violent than anyone had imagined. Astronomers found planets with toxic atmospheres, surfaces baked or frozen, worlds where storms rage for centuries and pressures would crush any human-made vehicle. They discovered that stars explode as supernovae, releasing more energy in a moment than our sun will emit in its entire lifetime. They identified black holes, regions where gravity is so intense that not even light can escape. Space, when seen through these instruments, remained beautiful, but became clearly hostile. It was not a serene dome painted for human beings. It was a vast arena of extreme physics. This created a strange psychological tension. On one hand, the more people learned about the universe, the more insignificant human life seemed in comparison to the ages of stars and the size of galaxies. On the other hand, curiosity did not fade, it intensified. Each discovery raised new questions. If Earth is not the center, what is? If the sun is just one star, how many more are there? If other planets exist, can any of them host life? The very facts that should have made us back away instead pulled us forward. Exploration always came with a kind of existential shock, a reminder that the universe is not obligated to be comfortable or understandable. And yet, humans kept going. Ships sailed farther, telescopes grew larger, probes were launched, astronauts left the atmosphere. Curiosity kept pulling us toward danger. That is the pattern you need to hold in your mind now. A species that once used the stars merely to survive slowly turned those same points of light into questions about origin, fate, and meaning. You live at a moment in that story where the myths have been replaced by physics, but the emotional response is the same. You look up, feel that the sky matters, and cannot quite explain why. You will bring that feeling back down to Earth and confront a more unsettling realization. Even here, on the planet that shaped you, safety is far more fragile than it seems. Bring your attention back down to the ground beneath your feet and ask a disturbing question. If the universe is so hostile, is Earth truly safe, or is that feeling of safety an illusion carefully maintained by a very thin set of conditions? From space, Earth looks like a solid, inviting world, a blue and white sphere that seems made for life. But humans can actually survive unaided only on a thin surface layer of this planet. Most of Earth is instantly lethal. About 71% of the surface is covered by ocean. Step off a boat in deep water without preparation, and you have minutes at best before exhaustion, hypothermia, or drowning end your life. The oceans regulate climate, store heat, and support ecosystems, but for an individual human body, they are not a habitat. They are a barrier you float on the edge of. Even on land, the picture is not as comforting as it seems. When scientists classify terrain by climate, altitude, and resources, only a fraction of land is truly suitable for long-term human settlement. Deserts, high mountains, ice sheets, wetlands, and extreme climates greatly limit where people can live without heavy technological support. That is why only a little over 40% of Earth's land area is considered directly habitable. Outside those regions, you face shortages of water, food, breathable air, or stable temperatures. Heat waves, blizzards, droughts, and storms are not rare exceptions. They are normal expressions of a dynamic climate system. The atmosphere that makes life possible is itself a fragile layer. It is only a few tens of kilometers thick, where it is dense enough to breathe. Climb just a few kilometers upward, and you begin to feel the drop in pressure. At around 8 kilometers above sea level, the so-called death zone in mountaineering, the air is too thin to support human life for long without supplemental oxygen. Go higher, to around 8 to 10 kilometers, where airliners cruise. An exposure without protection leads to unconsciousness in seconds and death shortly after. By an altitude of roughly 5 miles, the air is already too thin for unprotected humans to survive. Your lungs cannot pull in enough oxygen. Blood oxygen falls. Consciousness fades. Temperature and pressure add further constraints. Expose your body to very high heat and proteins begin to denature. Expose it to extreme cold and ice crystals form in tissues and fluids. High-pressure environments, such as deep underwater, can crush gas-filled spaces in the body and cause nitrogen narcosis or decompression sickness. Low pressure, as in near-vacuum environments, allows fluids to boil at body temperature and causes rapid swelling and unconsciousness. Earth constantly cycles through earthquakes, volcanic eruptions, hurricanes, floods, and impacts from space debris. Life persists because it has adapted, not because the planet is gentle. Notice how similar this language sounds to what you heard about space. Zero forgiveness. Narrow survival window. Dependence on a few key parameters. The difference is that on Earth, gravity holds a layer of air and water close to the surface, creating local pockets of stability. Gravity keeps your body anchored. It stops your atmosphere from drifting away. It shapes the oceans and keeps them from evaporating into space. Without it, there would be no breathable layer, no liquid water at the surface, no comfortable temperature range. Yet gravity itself does not care about life. It is simply the geometry of mass and space. What this means is that your sense of safety is largely a product of scale and habit. You live so deep inside this narrow habitable shell that you forget how thin it is. A few kilometers up and you suffocate. A few kilometers down into the ocean and you are crushed. A few degrees of global temperature change and entire ecosystems begin to fail. Earth is not a padded room designed for your comfort. It is a planet where conditions just happen, for a limited time, to align with the chemistry of your body. Seen from that perspective, survival here feels less like a guarantee and more like a cosmic coincidence. You exist in a brief interval on a single world whose environment is only marginally stable and constantly shifting. Beyond this thin biosphere, the hostility of space begins almost immediately. There is no warm transitional zone. There is only atmosphere, then vacuum. You are not as far from Bruce McCandless as you might think. He floated a few hundred kilometers above the surface, but in terms of survivable conditions, he was just one step beyond the edge of the same fragile bubble that keeps you alive right now. So ask yourself this: if even Earth, the only place you know where life thrives, is mostly deadly, once you step outside a narrow band of conditions, what chance do you have elsewhere? What happens when you leave not just your city or your climate zone, but your planet? You will take a guided tour of your own solar system and discover that every other world nearby is not a second home waiting to be claimed, but a carefully constructed death trap. Imagine you have a spacecraft that can drop you onto any planet in the solar system with no protection at all, no suit, no vehicle, just your body, your lungs, and your very limited tolerance for temperature and pressure. Your journey is not a tour of vacation spots. It is a sequence of ways to die. Start with Mercury, the innermost planet. There is almost no atmosphere, so there is nothing to breathe and nothing to spread heat around the globe. On the day side, the surface can reach temperatures hot enough to melt metal, well above 400 degrees Celsius. On the night side, without air to hold heat, temperatures plunge far below freezing. If you appeared there, you would suffocate in seconds because there is no oxygen. On the starlit side, your tissues would cook. On the dark side, your body heat would radiate away so efficiently that you would freeze. There is no safe zone, only brief delays in how you die. Move outward to Venus and the situation becomes even more extreme. Venus is almost the same size as Earth, but its atmosphere is a crushing blanket of carbon dioxide with clouds of sulfuric acid. At the surface, the pressure is about 92 times what you feel at sea level on Earth, comparable to being almost a kilometre under the ocean. The temperature is hot enough to melt lead, around 460 degrees Celsius. Step out there, and you would be crushed and incinerated almost instantly. Metals soften. Electronics fail in minutes. Human tissue would not last even that long. Mars looks friendlier in pictures, with its rusty plains and thin clouds, but that friendliness is an illusion. Its atmosphere is mostly carbon dioxide, and less than 1% as dense as Earth's at the surface. There is not enough oxygen to breathe, and there is not enough pressure to keep water in liquid form at normal temperatures. A human exposed on Mars would lose consciousness quickly as fluids in the lungs and eyes began to boil. Temperatures are often far below freezing, especially at night and near the poles. Even near the equator at midday, where it can briefly feel almost mild, the lack of breathable air and pressure would kill you long before temperature did. Now consider Jupiter. It is a gas giant, mostly hydrogen and helium, with no solid surface in the usual sense. If you tried to descend, you would fall into layers of thicker and thicker gas. Pressure and temperature would increase relentlessly as you went down. Eventually, the pressure would become high enough to crush any human body and even most spacecraft. There is no ground to stand on, no stable platform. The same is true for Saturn. Beneath the striking rings lies a deep atmosphere laced with hydrogen, helium, and compounds like ammonia. Inhaling that environment would burn your lungs with chemistry that does not belong inside a human chest, and long before that, the low temperatures and lack of oxygen would have ended you. Farther out, Uranus and Neptune orbit in the cold outer reaches of the solar system. Both are ice giants with atmospheres of hydrogen, helium, and volatile compounds such as methane. Their upper layers are extremely cold, with temperatures far below any natural condition on Earth's surface. Expose your body there, and the heat would be sucked from you rapidly. As you fell inward, pressures would rise, ices and gases would mix in exotic states, and any familiar biological structure would be destroyed. You would not simply freeze. Your tissues would become rigid, shattered by the combination of cold and pressure, like glass under stress. Between and beyond these planets, the vacuum of space waits. There is no air to breathe, no pressure to support liquid water, and no natural source of heat your body can use. If you were ejected from a spacecraft without a suit, you would lose consciousness in seconds as oxygen in your blood ran out. Your skin would swell because of the pressure drop, but you would not explode. Instead, you would experience a brief, disorienting interval, and then nothing, while your body cooled and drifted. Space does not welcome visitors. It does not reach out to catch you. It simply lets physics take its course. When you see photographs from orbit or robotic missions, it is easy to feel that these worlds are destinations waiting for human footprints. But when you strip away technology, each world is a specific configuration of lethal conditions. Mercury roasts and freezes. Venus crushes and burns. Mars suffocates and desiccates. Jupiter and Saturn offer only crushing gas layers. Uranus and Neptune offer cold and pressure that tear matter apart. Earth begins to look less like a typical planet and more like an anomaly. So now, place yourself back in that mental spacecraft. Having visited each world without any protection, there was not a single place where you could stand, breathe freely, and survive more than a few moments. The solar system is not a collection of alternate homes. It is a ring of death traps around a single, fragile oasis. And yet, humans keep building machines to touch these worlds, to map them, to land on them. Why? What drives a species to reach into such hostility, knowing how easily it can be killed? To answer that, you need to step back again and look not just at places, but at distances, and ask a deeper question. How big is the space that contains all of this? You must confront something even more difficult for the human brain to handle. The scale of the stage on which all of this is happening. Start close to home. Light from the sun takes about 8 minutes to reach Earth. That means, when you look at the sun with proper protection, you are not seeing it as it is now, but as it was 8 minutes ago. Light is fast, about 300,000 kilometers every second, yet even at that speed it needs time just to cross the gap between the sun and your planet. To leave the solar system entirely, light needs hours. A radio signal sent from Earth to a spacecraft near the outer planets can take many hours to arrive, and the reply takes just as long to come back. Even your own star system is large enough that communication is never truly instantaneous. Now step out to the nearest star beyond the Sun, Proxima Centauri. It is roughly 4.2 light-years away. A light-year is the distance light travels in 1 year, so a beam of light leaving Earth today would arrive there more than 4 years later. A spacecraft using present-day propulsion would need tens of thousands of years to cross that distance. In human terms, 4 light-years sounds like a small number. In physical terms, it is a gulf so wide that no existing civilization on Earth has ever sent anything close to crossing it. Your home galaxy, the Milky Way, is wider still. From one side of its disk to the other is on the order of 100,000 light-years. If you could travel at the speed of light, it would still take 100,000 years to go from edge to edge. That is longer than the entire span of what is usually called human civilization. When you see an artist rendering of the Milky Way with a tiny arrow saying you are here, what that arrow hides is that even nearby regions of your own galaxy are effectively unreachable with any technology you currently possess. Beyond the Milky Way lies the Andromeda Galaxy, the nearest large neighbour. Its light takes about 2.5 million years to reach you. When that light left Andromeda, early humans did not exist. Your entire species emerged, spread, built cities and invented telescopes during the time that light was in transit. Andromeda and the Milky Way are part of a small community of galaxies called the Local Group, spanning a few million light-years across. Already you are dealing with distances so large that ordinary numbers feel empty. On larger scales, galaxies cluster into vast structures. The Virgo supercluster contains thousands of galaxies and stretches tens of millions of light-years across. Even that is not the end of it. The supercluster itself is part of an even larger flow of matter called Laniakea, a region of space about 500 million light-years wide, where tens of thousands of galaxies move together in a kind of gravitational river. Between these structures lie enormous cosmic voids, regions so empty that crossing them at the speed of light would take hundreds of millions of years, with almost nothing to see along the way. Finally, consider the observable universe as a whole. From your position on Earth, you can in principle receive light that has been travelling for as long as the universe has existed. When cosmologists calculate the current size of that observable bubble, they find that it is about 93 billion light-years across. That number is not a metaphor. If you could freeze cosmic expansion and place a measuring rod from one side of your visible universe through Earth to the other side, you would get on the order of 93 billion light-years. And yet, because the universe is expanding, and because of the way light travels through that expanding space, you can never visit most of what you see even in theory. This is what it means for the scale to break the brain. Distances are so large that human intuitions about travel, contact and communication fail. The solar system that already feels wide and empty is just a minuscule pocket inside a galaxy, which is one among billions in a structure spanning tens of billions of light-years. You live in a tiny, fragile bubble of habitability, separated from almost everything else by gaps that even light struggles to cross. So now combine all of this, a universe where almost every location is hostile, almost every distance is immense, and almost every region is forever beyond your reach. The natural question that begins to form is this: in a cosmos this vast and this old, filled with so many stars and planets, are you really alone? And if you are not, what kind of neighbours could exist in a universe that treats life with such indifference? That is the question you will face next. A deeper, quieter question rises. In all of that, are you alone? Or is something else out there, thinking, building, fearing, wondering, just as you are? Both answers lead to a kind of terror. Astronomers now know that planets are common. Surveys of exoplanets show that many stars host multiple worlds, and there may be more planets than stars in the Milky Way galaxy. Even with very conservative assumptions, simple probability suggests that the universe likely contains billions of planets in total, perhaps far more. If only a tiny fraction of those worlds have the right conditions, that still means an enormous number of possible homes for chemistry to begin assembling into life. It is difficult to reconcile that abundance of real estate with the idea that only one world ever produced living cells. Yet you do not see alien ships filling the sky. You do not receive clear signals from distant civilizations. Your radio telescopes pick up natural emissions from stars, galaxies and gas clouds, but no unambiguous artificial beacons. There is no obvious galactic network, no visible signs of megastructures around stars, no known object that can be confidently labelled as constructed by non-human intelligence. The instruments become more sensitive each decade, the catalogues grow thicker, and still the silence remains. This is where the paradox becomes unsettling. If life exists elsewhere, then somewhere in that darkness there may be beings with their own technologies, their own survival instincts, and their own ways of expanding. Some might be peaceful, some might be indifferent, some might see new biospheres as opportunities or resources. A universe with other intelligences is not automatically a friendly neighborhood. It could be crowded with dangers humanity does not understand and cannot predict. The same curiosity that pushes you to explore might motivate others, and not every form of curiosity is gentle. At the same time, consider the opposite possibility. Suppose that, despite the number of planets and the age of the universe, life is extremely rare. Maybe the origin of life itself is an event so unlikely that it has happened only once in the observable universe. Or maybe simple life is common, but the leap to complex tool-using, technologically capable intelligence is almost never made. In that scenario, Earth is not just one living world among many. It is a solitary island of awareness in an ocean of unknowing matter. Humanity is then not a member of a crowded community, but the only voice in an enormous, mostly dark theatre. If that is true, the silence you observe is not a gap waiting to be filled by contact. It is the permanent background state of a universe that can produce stars and galaxies with ease, but almost never produces minds that can look back and ask why. The terror here is not invasion, but isolation. No help coming from outside. No older civilization to guide you, warn you, or share its mistakes. If you destroy yourself, or if some catastrophe wipes out life on Earth, the only known awareness in this entire observable volume may vanish. Both possibilities are frightening. If you are not alone, then you must wonder what else is out there, what it wants, and whether your presence has already been noticed. If you are alone, then the responsibility resting on your small, fragile species becomes almost unbearable. You carry the only known thread of memory, meaning, and reflection in a cosmos that would otherwise be indifferent and silent. Either way, there is no cosmic protection system. There is no guarantee that advanced civilizations live long, communicate clearly, or choose to reveal themselves. Right now, all you can say with confidence is this: you inhabit a universe old enough and rich enough in planets to make life elsewhere plausible, but you have no proof of neighbors. Your telescopes hear only the faint hiss of natural processes. Your detectors see only stars and galaxies behaving according to physics, not messages written across the sky. The silence itself becomes a signal, one that forces you to consider filters, dangers, and the fragility of intelligence. So you stand on a tiny world in a lethal universe, asking a question with no easy answer. Are you early, one of the first to awaken in a mostly sleeping cosmos? Are you late, living after many others have already risen and fallen? Or are you alone, speaking into a darkness that will never answer? To push closer to that mystery, you need to ask an even sharper question. If life can arise, what stops it from spreading everywhere? What kills civilizations before they can fill the sky? That is where the idea of a great filter comes in, and it changes how you think about your own future. You have just asked why the universe is so silent despite its age and scale. That question naturally leads to an unsettling idea. Maybe the silence is not an accident. Maybe there is a barrier that almost no civilization crosses. This idea is often called the Great Filter, and once you understand it, it will change how you see human history and the future. Start with something simple. Life on Earth did not jump from raw chemistry to technological civilization in a single step. It moved through a chain of stages. First, non-living chemistry on the young Earth somehow organized into self-replicating molecules and primitive cells. That step alone may have taken hundreds of millions of years. For a long time, life remained single-celled. Microbial mats and simple organisms dominated the planet for billions of years. Complex multicellular life, with differentiated tissues and organ systems, appeared only much later, in roughly the last billion years of Earth's 4.5 billion year history. Even after multicellular life emerged, intelligence of the humankind took an extraordinary amount of time to appear. Dinosaurs ruled the land for more than 100 million years, without ever building radios or telescopes. Many species evolved complex behaviors, social structures, and problem-solving abilities, but only one lineage of primates eventually developed symbolic language, cumulative culture, and technology that can alter an entire planet. Intelligence in the human sense may be an unstable, fragile outcome, not a guaranteed endpoint. Now imagine that at each of those transitions there is a cosmic gate that is very hard to pass. Perhaps the origin of life itself is extremely unlikely. Perhaps the emergence of multicellular organisms almost never happens. Perhaps the development of brains capable of abstract reasoning requires such specific evolutionary paths that almost no planets produce it. In that case, the great filter could be mostly behind you. Humanity would be one of the rare success stories that made it through a gauntlet that destroyed or stalled countless other attempts. But there is another possibility that feels more dangerous. Maybe the early steps, from chemistry to simple life, and even to multicellular organisms, are not so rare. Perhaps the real filter comes later, after intelligence appears. A species that discovers fire, metal, industry and computation also discovers weapons, ecological disruption, and powerful technologies that can alter its environment faster than it can understand the consequences. Civilizations might tend to expand, exploit resources, and build complex systems until they destabilize their own foundations. Collapse could come from many directions at once. Resource exhaustion is one obvious route. A civilization might consume its accessible energy sources, destroy critical ecosystems, or destabilize its climate faster than it can adapt. Another route is self-inflicted catastrophe through advanced weapons. Once a species can build nuclear arsenals, engineered pathogens, or uncontrolled artificial intelligence systems, it holds tools that can end its own story in a very short time. Add to this the possibility of cosmic disasters. Supernova explosions, gamma-ray bursts, or large asteroid impacts can sterilize regions or reset biospheres. Predatory civilizations, if they exist, would be yet another threat, hunting for emerging competitors. If the great filter lies ahead, then most civilizations that reach a level similar to yours may not survive for very long afterward. They may self-destruct, be destroyed, or simply fail to manage their own technologies and environments. From a cosmic perspective, they flare briefly and vanish, leaving behind no lasting megastructures, no enduring signals, no grand empires spreading across galaxies. The universe would then be full of planets where life began, maybe even where intelligence briefly arose, but almost none where it endured long enough to become visible on interstellar scales. This is what makes the concept so unsettling. You do not know where the filter is. If it is mostly in the past, then you are extraordinarily lucky, part of a tiny fraction of life that has made it this far. If it is mostly in the future, then you are approaching a dangerous region of parameter space, where many others have likely failed. Survival might not be the default. It might be the exception that requires unusual levels of cooperation, foresight, and restraint. Look at your own time in history, and you can feel this tension. In just a few centuries, humanity has acquired the ability to alter the climate, extinguish species, and build weapons that could end global civilization. It is also beginning to develop artificial intelligence, genetic engineering, and other transformative technologies whose long-term effects are not fully understood. You are living at the moment when your species may either learn to pass through this potential filter or become one more silent data point in the background statistics of the universe. So, when you think about the Great Filter, you are not just contemplating alien civilizations, you are looking at a mirror held up to your own future. The question it forces on you is simple and brutal. Are you a rare survivor that has already overcome the hardest obstacles, or are you racing toward the real test that almost no one passes? To answer that, you have to step back once more and consider an even colder perspective: time itself, and how brief any civilization really is against the age of the universe. Even if a civilization passes every environmental and technological test, it still has to confront a quieter, implacable enemy that never stops advancing. Time. Start with species, not galaxies. Paleontologists studying the fossil record estimate that the typical lifespan of an animal species on Earth is on the order of 5 to 10 million years before it either evolves into something new or goes extinct. That might sound long, but compare it with the age of the universe, about 13.8 billion years, and you realize that any given species is a brief flicker. Humanity in its modern anatomical form has existed for roughly a few 100,000 years. Human civilization with cities, writing, and complex technology occupies only a few thousand years. On the scale of cosmic time, that is thinner than a line of ink on a very long page. Now imagine intelligent civilizations scattered through time as well as space. Each one appears, struggles, builds, and disappears within a window of perhaps tens or hundreds of thousands of years as a technological culture. That is generous and still tiny compared to billions of years. The odds that two such civilizations happen to exist in the same region of space and the same narrow slice of time, and then also manage to notice each other across light-year distances, are not as large as your intuition might suggest. Many may rise and fall alone, never overlapping in a way that allows for contact. Meanwhile, the universe itself evolves. Stars burn their nuclear fuel and die. Massive stars live fast and explode as supernovae after only a few million years, seeding space with heavy elements but ending their own stability. Smaller stars like the Sun last, for billions of years but not forever. Eventually they exhaust their hydrogen and swell into red giants before collapsing into white dwarfs that slowly cool. Over even longer timescales, star formation in galaxies declines as gas is used up or expelled. The bright, busy universe you see today is a temporary phase. Time also erases information. Geological processes recycle planetary crusts, burying or destroying traces of past events. Erosion, tectonics, and chemical weathering wipe away surface structures. In space, radiation degrades materials, orbits change, and collisions break objects apart. Given enough time, almost any physical artifact becomes dust or is scattered. Even if an ancient civilization filled its planetary system with monuments, after hundreds of millions or billions of years, those traces could be gone or rendered unrecognizable. You could be looking at worlds where something once happened without any clear evidence left. If the cosmos had a single lesson to teach, it might be this: nothing lasts forever. Galaxies merge and change shape, orbits shift, stars fade. Black holes slowly evaporate over unimaginable timescales. Entropy, the tendency for systems to move from ordered states to disordered ones, steadily increases. Against that backdrop, a technological civilization is a short-lived structure of low entropy, holding back chaos for only a moment before it breaks apart or transforms. Think about what that means for you right now. You live in a thin slice of time where Earth still has abundant liquid water, the sun is stable, and the sky is full of visible galaxies. You live after life has had time to evolve intelligence, but before the stars have grown too old and the universe too cold. You occupy a narrow temporal window that allows questions about origin, structure, and fate to even be asked. Outside this window, the conditions for such questions may not exist. This perspective makes the Great Filter even more daunting. It is not just that civilizations might destroy themselves through technology or be erased by cosmic accidents. It is that, even if they avoid those fates, they are still transient patterns in a universe that measures time in billions and trillions of years. Time is patient. It can wait out any burst of activity, any brief age of exploration, any golden era of science and art. So here is the thought that should unsettle you. Even if the universe has hosted countless civilizations across its history, most of them are probably gone. Their signals have faded, their structures have decayed, their stars may have died. You might be arriving late to a party whose decorations have already blown away. Or you may be early, one of the first guests in a cosmos that will host many more, long after you are dust. In either case, your own moment is short.